Okay, let's continue with section 1.9. Okay, so 1.9 is on exact differential equations. Okay, so let's find a definition of this, exact differential equations. So definition, the differential equation okay, m of xy dx plus n of xy dy is equal to 0. Okay. Okay, is said to be exact in a region R if there exists a function b of xy such that d phi dx is equal to m, and d phi dy is equal to n for all xy in R. Okay. P of xy is called the potential function. And that's similar to a conservative vector field in Calc 3. Okay. So, okay, theorem. Okay, test for exactness. Okay, or a test for conservativeness. Okay, m of xy dx plus n of xy dy is equal to, I'm sorry, is exact. Well, 0 is exact for all xy in R, if and only if the derivative of m dy, the partial, I should say the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. Okay, so if those are two equal, then it's an exact equation, or what we call in a vector field, it's a conservative vector field, and there exists a potential function then. Okay. Okay, so let's figure out how we could solve this. Okay, determine a solution. Let's solve a differential equation using this exactness. definition. Okay, determine the general solution to y over x dx plus natural log, plus 1 plus natural log of xy dy equals 0. Okay, so first I want to see if this is an exact equation. And then let's go about figuring out what the potential function of that is, of that exact equation is. Okay. Okay, and that potential function will help me solve the differential equation. Okay. Okay, so we want to test for exactness. So we want m sub y. Okay, or that's the partial derivative with respect to y. Okay, so m is y over x. And so okay, the partial of y over x with respect to y. Okay, so we treat x as a constant. To take the derivative with respect to y, we get 1 over x. Okay, now we want the partial of n with respect to x. So that's the partial of 1 plus natural log of xy with respect to x. Okay, so the partial with respect to x, well, 1 is just 0. Okay, the natural log of xy, that's going to be 1 over xy times, okay, this is chain rule, times the inside, but y is just a constant. So the derivative of xy, if y is a constant, is just y. Those cancel, and I'm left with 1 over x. So yes, it is exact. Okay, so it checks. Okay, so how do we find the exact, the solution to this differential equation? Okay, this exact differential equation. So I know that m, okay, m is equal to d phi d theta, or sorry, d phi dx. Okay, and that's equal to y over x. Okay, so if I took this potential function, okay, and m would equal to this, the partial of the potential function, whether take the derivative with respect to x, and it's going to be y over x. Okay. Okay, so if I kind of integrate, okay, I would get phi of xy. Remember, I'm integrating with respect to x, and y is just a constant in this case. Okay, then I get y times the natural log of x. Okay, so y times the natural log of x, but then I could have some constant c, but that constant could be a function of y, because remember, all y's are just constants. So let's call that maybe g of y. Okay, and then we could have actually a constant function, and we'll call that k. Okay, so we could have had a g of y. If I take the derivative of this with respect to x, the only portion of this to survive is going to be that y natural log of x portion. The g of y would go away because it's treated like a constant, And the k would go away because it is a constant. Okay. Okay, but we're going to let k go to 0 because we only need one potential function. We don't need a family of functions. We just need one potential function. Okay. Let k equal 0 since we only need one potential function. Okay. So now let's look at n. Okay, n is equal to d phi dy. Okay, partial of phi with respect to y. And that was equal to 1 plus natural log of xy. Okay. Okay, so we're going to integrate this guy, but with respect to y. Okay, integrate him with respect to y, leaving x as a constant here. Okay, so what I'm going to do here is I'm going to break up this natural log of xy. That's going to become 1 plus natural log of x plus natural log of y dy. Okay. Okay. So that's going to be equal to, okay, the integral of 1, okay, that just becomes y. The integral of natural log of x, that's just a constant, and so that's just going to be natural log of x all times y. Okay, plus the integral of natural log of y, okay, that is y times the natural log of y minus y, which is just y times natural log of y minus 1. Okay. And once again, we could say, this is phi of xy, potential function, okay, of xy. We could once again say that there could have been, say, an h of x, and then plus a k. And then once again, we're going to let k go to 0. There could have been an h of x here that we just don't know, that didn't have a y value. So when I took the partial with respect to y, it just kind of disappears. Okay. Okay, so let's distribute the y there, and we're going to get this to be equal to phi of xy is equal to y plus y natural log x plus y natural log y minus y. Okay, that's nice. Those y's are going to cancel. Plus h of x. Okay, and so we get phi of xy equals y natural log of x plus y natural log of y plus some h of x. Let's compare this to what we got before when we took m with respect to x. There was y natural log of x plus some g of y, right? But there wasn't any value that just included x. Okay, so there is no h of x. Comparing the two, compare the results. You get phi of xy equals y natural log of y plus g of y. Well, what do you think g of y is here? Well, g of y is going to be the y natural log of y. It just includes, y natural log of y. Okay. That's the g of y. It only includes things that involve y into that term. So of course, that's going to go to 0 if I take the partial with respect to y. I'm sorry, take the partial with respect to x. If I take the partial with respect to x, that thing goes to 0. Okay, the y natural log of y. So you get y natural log of x plus g of y. Okay, and h of x, there is no h of x is 0. Okay. And so what was the g of y? The g of y was what it is above. And so the potential function of xy is equal to, okay, is equal to y natural log of x plus y natural log of y. Okay. Okay, I could factor out the y, and I would get natural log of x plus natural log of y, and then I could combine that using the property of natural logs. That's y natural log of xy. Okay, so p of xy equals y natural log of xy. Okay, so now let's go back to the beginning. Okay, we found our potential function, but how does that help me solve my differential equation? Okay, we found the potential function, and it says that we have something with respect to x plus m with respect dx and dy is equal to 0. Okay, so the derivative of this potential function, okay, the derivative of this potential function was equal to y, I'll say the potential function of xy was equal to 0. Okay, so the derivative of the potential function was equal to 0. Therefore, if I were to integrate, I would get the potential function xy to be equal to a constant. Okay, because going again back to the original statement, we had yx dx. Okay, that's the potential function that's going to get me the partial with respect to x, the partial with respect to y. Okay, but if I take the derivative of that, that equals 0. So what would the potential function? The potential function would equal a c, or equal a constant. Okay, I'd have to take the derivative of both sides, and that of that potential function. That would equal 0. So that's just going to equal c. So I would just get y natural log of xy is equal to the constant c. Okay, so that's how I find the general solution. So what if something isn't exact? Can we make it exact? Can we turn it into exact? Okay, so what if it is not exact? I'll say a differential equation is not exact. Can we turn it into one? Okay, and yes, we can. If it satisfies a condition, okay, for m of xy dx plus n of xy dy is equal to 0. Okay, there exists an integrating factor So if there exists, I'll write that out in words so you have it. If there exists an integrating factor that depends on x, okay, if and only if my, the partial of m with respect to y, minus nx, the partial with respect to x, over n is equal to some function of x. Okay. Okay, where f of x is a function of x only. Okay, in such a case, the integrating factor is I of x equals e to the integral f of x dx. Okay. B. There exists an integrating factor I'll put an if there. If there exists an integrating factor that depends only on y, if and only if m of y minus n of x over m this time, okay, is equal to f of y, a function of y only, okay, in such a case, the integrating factor is, and make sure you catch this, is I of y equals e to the negative integral of g of y dy. Okay, so that's due to the nature of how the integrating factors behaved. Okay, so see how this works in practice. Okay, number 2, solve 2x minus y squared dx plus xy dy is equal to 0. Okay, is it exact? Well, let's find out. Okay, my is equal to what? That's the derivative partial on m. Okay, so this is m, this is n. Okay, the partial on n with respect to y, that's just going to be 2y, or negative 2y. Okay, nx, the partial of n with respect to x, what's that going to be? That's just going to be take the derivative with respect to x of n, and that's just y. Okay. So, however, what would happen if we did, say, m? Now, that's not exact, right? Not exact. But if we look at this, that just has things in terms of y. That's kind of interesting. And so if we do my minus nx and put that over n, okay, then I get negative 2y minus y over xy. And so that's negative 3y over xy. And lo and behold, we get negative 3 over x. And that is just a function of x only. We'll call that f of x. Okay, and they're saying that there exists an integrating factor, okay, such that, okay, I of x is equal to, now this integrating factor is not the same one as we used in the linear differential equations, but it poses the same type of operation that we use, and I'll get to that in a minute. Okay, it just helps me to turn something that was not exact into something that is exact by multiplying through by that value. So that's e to the integral of f of x dx. So this is going to be f of x dx, which is e to the negative 3 over x dx. So this is going to be pull the negative 3 out, that's a natural log. That's e to the negative 3 natural log of x. So that's just going to be x to the negative third power. Okay, after the natural log and the e cancel out. Okay, and so let's take this guy and multiply him through our original differential equation here. X to the negative 3 times 2x minus y squared dx plus xy dy is equal to 0 times x to the negative third power. Okay. So distribute. Okay, and we're going to get, can distribute inside here as well. 2x to the first times negative third, that's x to the negative second, minus x to the negative third y squared. That's going to be dx. Plus, this is going to be x to the negative second y. dy is equal to 0. Okay, now let's try this again. Let's try this process over again. What's my? Okay, again, this is my new m. This is my new n. Okay. And so m with respect to y, well, the first term goes away because there's no y involved. And the y squared is going to become negative 2x to the negative third y. Okay, so that's my. Okay, n with respect to x is going to become negative 2 x to the negative third y. So now it is exact. Okay. So now I want to find my potential function. Okay. So we now know that it's exact. We want to find the potential function here of this new equation that we found. This new exact equation that we found. Okay. So we know that the partial of phi with respect to x is equal to m. Yep. Partial of phi with respect to x dx is going to be m, which is equal to 2x to the negative 2 minus x to the negative third y squared. Okay. Okay, I want to integrate this with respect to x. Okay, so my potential function in terms of xy is going to be equal to add 1 to that power, that's -1. Divide by -1, that's -2. X to the negative first power. This one, the y is just a constant. So this is going to be -2. Divide by -2, I get positive x to the -2. Positive, I think it's 1/2, right? 1/2 x to the -2 y squared. And this could have had a g of y, okay, plus a k, but we're going to get rid of the k. Let k go to 0. Okay, now d phi dy was n, okay, and n in this case, for this new exact equation that we created, okay, was equal to x to the -2y. Okay, and we're going to integrate that with respect to y. Okay, on y, treating x as a constant. So this just becomes, okay, phi of xy is equal to x squared, or x to the -2, y squared over 2, plus some function of x, okay, plus some k, which again, we're just going to let the constant go to 0. Okay, and so if we compare these two, okay, we have this guy here with some g of y, and then this guy here with some h of x. Well, g of y doesn't exist. There is no y value that comes out in the second equation here. So g of y doesn't exist, but h of x does exist because this is a term that depends only on x. Okay, and notice that they do have a term in common. This x to the -2 y squared over 2 term, that is the same term. Okay, that's kind of cool. So we know that the potential function x of y is equal to, okay, I can write this as 1/2 x to the -2 y squared minus 2x to the first power. Okay, so that was my potential function. Okay, and once again, if I take the derivative of the potential function, okay, that gives me 0. Okay, so if I integrate, okay, that's going to give me the potential function equal to c. Okay, so, and so I can just set this guy here equal to c, and that will be my solution. Okay. If I really want to solve for y or y squared, I can do that as well. Okay. So let's see what we get here. I could multiply everything through by an x squared. Let's do that. Okay. That becomes 1/2 y squared minus 2x is equal to cx squared. Okay. And then we can multiply through everything by 2, I guess. Okay, I'll call this C1. Okay, because I'm going to multiply through everything by 2 now. And so we're going to get y squared minus 4x equals 2c1. I'm going to let 2c1 equals c2. So C2x squared. Okay, and then I'm going to toss this negative 4x to the other side. So I get y squared equals C2x squared plus 4x. Okay, and I'll just let C2 be C. Okay, just be some generic constant, Cx squared. Okay, and I could take the square root of that, plus or minus, if I really wanted to. I could toss the x squared to the other side, however you want to do it. But we could solve it like that. Okay. Okay, and that is 1.9. That's the end of chapter 1. I'll see you in the next chapter.